good afternoon, and thank you very much. I'm very glad that I can be here today. And I think that although maybe on the surface it would seem that these are different topics, just as Jansi has brought out some of the things from the previous two speakers, I think now, although we're shifting to look at agriculture and food provision, we're still having some of those themes coming through. So my talk this afternoon is about crop climate models and how to develop advisories. This is at giving advice both to farmers on an operational level, to the agricultural extension practitioners, also usually from the government department, also to NGOs, but then also in the long term to how the agricultural policy should be formulated so that we can meet the SDGs relating to food and to the changing climate and climate actions. Let's see. Yes. I'm not sure. Can you see the top of my screen or not?
It says some basics.
Okay, you can. All right. Sorry, okay. I can only see something funny at the top there.
Okay.
So, yes, just before I start talking, I think us scientists have quite a lot of jargon. So I wanted to just explain a few things first. And one is that a model is a representation of the real world. So we try to make an idea of what is the real world. The second thing is that we hear about global climate models. These are GCMs, and they usually try to simulate all the different factors that are affecting the Earth's climate. And so if we think about them, it's a whole bunch of mathematical equations that are trying to represent the whole climate. And of course, the climate is then the interaction between the atmosphere and the land surface, but also with ocean and the sea ice, and all of those things together. Come on. And so if we think about it, then we can see that the way we can do it is by taking a three-dimensional model of the Earth and making grid cells right across the whole Earth. And then we do the exchange of energy, etc., from each one. And so we know that some of these factors don't change, like the distance from the shore, or the elevation, or the latitude. But some of the factors will be changing. We know that we have a seasonal cycle. We know we have a diurnal cycle. We know that the volcanic eruptions and air pollution can also influence the climate and the atmosphere all around the world. So if we just think about these little blocks on the Earth, then we could see that we need to do the energy balance. How is the energy being exchanged between the ocean to the atmosphere from the Earth? And we know that we take not only this grid at one level, but we can take it up to 200 levels into the atmosphere. And so this then helps us to simulate thunderstorms, etc. But you can see how many grids there are, and they're rather large. So we also need to do some downscaling, and this is where we go to a regional climate model. And then we try to have values that are more like at 5 or 15 kilometer squares, so we can look at the local situation. So if we look at climate change across South Africa, we all know that it's warming. It's going to get hotter. And this is across the whole country. These six different models on the left-hand side are for a mean from 2041 to 2070, and on the right-hand side, 2071 and to 2100. So you can see that on the left-hand side, there's a range of between 2 to 3 degrees C, and on the right-hand side, maybe 3 to 5 degrees C by the turn of the century. And what implications is this for food production and agriculture? Probably there will be more frequent droughts, there will be more heat waves, and they will be of longer duration, and we've already seen this. There will be reduced soil moisture available. We will have perhaps a shorter growing season because of these above facts. We also might have a longer burning season during our dry winter across most of the Highveld. And So we could expect a reduced maize crop yield and possibly also reduced livestock production. So we need to deal with all of these things. So how can we help our farmers to maintain sustainable farming systems? Let's just look at the basics of temperature and its effect on crop production. So if we think of tropical regions, then here, this is for maize. We can say that if we at 3 degrees, we can expect up to maybe 20% reduction in the maize. If we take the wheat, then at 3 degrees increase in temperature, maybe again, we could say somewhere between 10 and 20% decrease in our production. It's interesting just to look at the temperate zones and see that the variation is more, and also that there's not a definite trend to decrease in production. And that is because sometimes the cold temperatures are limiting in the temperate zone, but for us in Africa, it's all in the tropical regions and warm temperatures. So to continue with my basics, our crop climate model is a bunch of mathematical equations, and they're taking and trying to represent the interaction between the air around the leaf and how it will produce something. So it's those interactions. And in these agricultural systems, we have a number of organization levels, from a single leaf, single plant, a field, up to a farm, or even the whole region or the nation. And so the aim of the crop models is to be able to estimate how much harvestable economic yield can we produce. And there's a bunch of different kinds of models that are used, and I won't go into all of those, but mostly we're looking at simulation and optimization models with some static and dynamic and deterministic pieces as well. So if we look at the crop modeling system here, you can see it's rather complicated a flow of energy and substance between the different parts, but each crop model will be for a specific crop, and usually we use a daily time step that goes through the season, and we need to have the inputs for the soil and for the crop characteristics as the standards, and then we would use the daily climate data from historic record. We also then can change the agronomic management practices. So this is about when they plow and how much fertilizer and those things. And although they've been developed around the world, they've also need to be calibrated for our own situation and validated for the different cultivars grown in South Africa. And you would make some kind of a one-to-one graph like this. So then we can predict the growth, the development, so shifting into reproductive stage, the yield, and how much water is needed. So if we think about these crop models, then we can see that there's some different uses. And the first one is as research tools. And I think my two colleagues who've presented already have also emphasized that research is what we need to continue to do. And this is very important so that we can continue to be monitoring and keeping up with the latest technologies. So we need to understand the whole system, and this needs to have a number of different disciplines, and we need to be able to analyze the yield and see what the genetic improvement is doing, and then do some data analysis. So this is really saying if we have new cultivars, then maybe the bread baking characteristics might be different or something like that. So we need to look at that continually. Then we can also use them as crop system management tools, and this would be more for the farmers or the farm managers. And so here we would be able to put in the agronomic practices and be able to show them how those practices would change something. So whether you add nitrogen or whether you do plowing or weeding at different times. And this then helps us to make some kind of a risk assessment. And we can also optimize for a particular site because the soil and the climate will be different at every different place. And then, of course, we can use it for policy also. And so we can use the model by running it for 30 or 50 years, be able to establish the best practice. and be able to see if, for instance, we're in a La Nina like this year and we have a lot of rainfall, what would have been our best advice in October? We can also do the crop yield forecasting and estimating, and we have a crop estimates committee, and we're waiting in anticipation now in February for their first estimate of what the maize crop will be like following this high rainfall season. And then we can also use it for all sorts of mapping systems. So we can use the crop climate suitability. So we know that certain crops need certain temperatures and certain amounts of rainfall. And we can use that then to see, as the climate changes, what alternative crops could we use. We also need to apply these climate changes to the local ecosystem conditions. And this can then give some advice to the policymakers. We can do the gap analysis. How different is our production at the moment compared to what the potential production is? And so we can use that for our long-term recommendations and our outlooks. So just a quick few examples. Here is mulch against yield and nitrogen level, low nitrogen, high nitrogen, and you expect to have higher production. Here, these are what we call CDFs, and you can see the difference between the La Nina and El Nino opportunities. We can also test different practices. So we can say under high rainfall, how will they perform? Or we can say under low rainfall or medium rainfall, how would they perform with different ploughing methods? Or we could even look at different cultivars. So this is comparing across the Southern African region. And we can see that this cultivar obviously is doing better in South Africa. And in Namibia, it is doing worse because it's a much drier and hotter situation. And so if we think about what are the gaps for this, specifically for diseases and pests, we know that there's no holistic or powerful enough model that actually explains the diseases. We're not able to stimulate the pests and diseases outbreaks. We don't have qualitative impact of the pests and diseases as yield reducing factors. Of course, what we do is we just say, well, the leaf area reduced, therefore the production will reduce, but this is not always a good logic. And so we also know that with the pests and diseases, there's a lot of variability across the fields. And so we can track this with the satellite images and also the yield with the precision agriculture as it's harvested. But we also need to be sure that we have the correct initialization points, and we need to be able to monitor and really observe with the latest instruments to be able to look at those infections of the diseases. So if we think about what kind of things could happen, we could use as interventions. We could check the different agronomic practices. Can we do crop rotation that will then reduce the number of diseases left in the soil? Can we use chemical control by spraying or doing fumigations? Can we use biological control agents, where we would use integrated pest and disease management and introduce some predators in that situation? Or can we be looking at breeding opportunities so that we can have, say, growth for higher temperatures or shorter seasons? And can we look at different answers for different regions across South Africa according to the rainfall, temperature, and the radiation? So what we need to do is we need to characterize the disease cycle of the infection chain and be able to say what is really happening and can we measure it, and then be able to relate this to the environmental conditions, so to the temperature, rainfall, leaf wetness. And so then we can come up with some kind of a process-based information, and this will constitute the building blocks then for the model and the model structure. And so if we think of some of the examples, we know we have wheat stem rust infections, and it's related to temperature, so above 20, favor stem and leaf rust, etc. Or we have soybean rust development, and here the temperatures are between 12 and 29. And also there need to be periods of leaf wetness. So in this year, when we've had so many rainy days, it's probably quite bad. If we think about the smut in the maize, then we know that the optimum temperature is 13 to 20 degrees. And if the soil temperature is above 25, then it'll be unfavorable. And then, of course, we also have downy mildew. And here we need to look at the hourly data and see how much, often the
sorry, just something quickly for you.
So if we,
I myself hadn't actually looked at the
early warning models. Sorry, can we just stop the interruptions? So we have this great compass, and this then takes the forecast and tries to predict when are the opportunities at different times for powdery mildew, downy mildew, and botrytis. We also have AgriCloud that gives the advisories for when an action should be taken by the farmers. And so it's for their specific region, and it also includes the weather observations and be able to tell them whether they can spray in the next few days. So what do we need? We need experimental results. We need the relationships between the crop growth and the disease infection. We need the weather parameters. We need the weather forecasts on a daily basis. And we need to have satellite monitoring of the fields. And then the output can be some routine advisories, which are very low location specific, can be messages sent to farmers, and there can be a good delivery system via cell phones to the client database. And so if we think about something that our first speaker also, Jabu, mentioned, and that was collaboration. We can't do this by ourselves. We need to have climate models, those GCMs, and we need the weather forecasts, for instance, from the South African Weather Service or from ECUMWF, and this needs to be downscaled to at least 15 kilometers square or to a field level. We also need the crop models for each different crop. We need to develop the disease and pest models and be able to integrate them with the crop models. And then the advisories need to be also developed so that there can be an early warning of any conducive weather conditions for infestation. There can be then advice for when to spray which pests and diseases. And so that for the wine farmers, they can reduce sometimes by 60% the number of sprays they do if they take it from just spraying every 2-3 days to look at the weather conditions. And so we can then have a monitoring of the favorable conditions. And so we really need to be able to do this all in transdisciplinary teams. Thank you very much.